Xavier, yeah. Okay. Thank you, Xavier. So today I'm going to talk about the topic of regret minimization. So it's something that comes from reinforcement learning. And here the idea is to try to see if we can use some automatic control tools in order to tackle this problem that is often met in reinforcement learning. So that's basically the presentation. I will start with the context. So we are going to assume that we have a true system and we would like to reject the disturbances of this system. And for that, we are going to do model-based control. But unfortunately, the optimal controller that will reject these disturbances is unknown because it depends on the true dynamics, which are unknown because of the presence of disturbances. So basically, one possibility you can do is to use model-based adaptive control. So every time you get a new data point, you can find a new estimate of your model, adapt your controller based on this, and then you go on and so on and so forth. And just here for the presentation, we are going to have for this, for the system identification ingredient we are going to consider, is that we will have the data from the beginning of the experiment. And we will also consider that we have a full order model structure for our system. So the true parameter vector will be denoted by θ0. Okay. And so then the problem is to look at what is the actual cost that we get, and we compare it with the optimal control cost we will get if we had the optimal controller here. And basically, because we have uncertainties on our estimates, well, we will have a difference of the control cost. And now how to, oh yeah, I have a problem with my computer now. Okay, now how to handle this problem of uncertainties. What you could do is to add a large external excitation here on your control effort, so that then you increase the signal to noise ratio. But then the problem is because of this external excitation, which is disturbing the input and the output, sometimes what you can get as an effect is a degradation of your control performances. So basically what we would like to find is a more appropriate external excitation, which will indeed give a decrease of the uncertainties and hopefully will decrease the difference between the actual control cost we get and the optimal one. And so this is where the concept of regret comes here. It's basically the function of both the exploitation and exploration cost to be minimized. So conceptually, you can define the regret as the difference between your adaptive control cost and the optimal control cost. So if you only look at the expected value at one time instant, you call that the instantaneous regret. And if now you take the sum from the beginning of all the instantaneous regrets, you call this the cumulative regret. And basically, the objective is to design the adaptive control algorithm, so the external excitation and the control design, such that you minimize the cumulative regrets. Okay. And here what we are going to consider is the classical linear quadratic problem, where here I have a state system. So I'm going to assume that all the states are measured, but you could extend this problem to non-measured states with a measured equation. So for this state system, we have a noise which is Gaussian distributed with a noise covariance sigma A. And as I said before, we have also a full order model structure. So I assume that here, I have a true parameter vector θ0. And here we would like to control this system with the infinite horizon linear quadratic control. So basically, it's to find this matrix, which will minimize this control cost here, where here you have the expected value taken with respect to the noise. And so here, sorry, I forgot to mention, we are going to take the case where we have only one input. Okay, and so we know how to compute this matrix K. You have to solve the discrete time Riccati equation, but this depends on your true parameter vector. So what you could do is to do the adaptive controller to tackle this problem. So at each time you get a new data, you estimate your parameter vector. So we are going to denote this θ hat t, and we are going to consider here the online least square estimator, or PEM. And here the controller here will be designed based on this parameter vector, and we add an external excitation that we will denote by B. Here in this case. And so here I'm going to consider this cumulative regret. So it's a regret that has been considered a lot in the literature in regret minimization. So you take the difference between this cost that you get with the adaptive control minus the cost that you get that you will get if you were implementing the optimal controller and you will not have also external excitation. So I'm going to denote by x tilde and u tilde this optimal state and input. And here the expected operator is taken with respect to E and V. Okay. And then the objective is to design the control policy. So how to compute my controller from the parameter vector and the external excitation sequence V such that I minimize this quantity at a given horizon capital T. Okay. There are several classes of adaptive control algorithm that has been considered in the literature to tackle that problem. The first one is based on the certainty equivalence principle, that you are going to assume that your estimate is the true parameter vector, and you design the controller accordingly to this. And we are going to use this notation in this case for the certainty equivalence control. And another class of algorithm you can find in this literature of regret minimization, so it's called optimism in the face of uncertainties. So because your parameter vector here is uncertain, here what you can do is that you can consider the parameter uncertainty and try to minimize the lower bound on the regret. So that's why they call it optimism, because we are going to go for the most optimistic case and try to minimize it by doing so. Okay. Mostly the result we have for this problem of regret minimization in the linear quadratic case is for the asymptotic domain. Many people try to see, to look at the different rates you can get for the regret in the asymptotic domain. And we know from many works, so here, for instance, two examples of works, is that the regret will either be square root of t, growing as square root of t optimally if both matrices here are unknown, so the state matrices A and B, and it will be log t if you know one of them, and you have to estimate the other one. Okay, and then how to reach these optimal rates? Then there are several algorithms for this. For the optimism in face of uncertainties, there is the Thompson sampling strategy that has been developed for this problem. So here you don't add external excitation, but the Thompson sampling works as follows. So what you are going to do is that you are going to keep the controller constant during several time instances until the estimated uncertainties are below a given threshold. And then you are going to generate a new controller, which is computing by randomly drawing a parameter vector in the uncertain set. And you do that by reiterating like this. Okay. And then the other type of algorithm you can find is based on the certainty equivalence principle, where you could consider an external excitation, which is a white Gaussian noise, for which the variance decreases as 1 over the square root of t. And so this will also guarantee a rate of square root of t, for instance, or log t, depending on which case you are. But then the question is, what about finite time regret minimization? Because in real life, we won't have infinite time. And this is not clear from the literature what we should do. And first question we could ask is this excitation actually optimal still in the finite time case? So that's what we want to see in this presentation. And I really have a problem with my mouth. Okay, and then so what we could look at is basically work that we have in the automatic control community, because basically regret minimization is an experiment design problem. And we know that from what we have been developing in the automatic control community is that we have tools to deal with the problem of designing a finite time excitation, minimizing the expected value of a given cost. And the idea of the problem or the approach of the talk here is to use the tools from this literature in order to develop a new algorithm for finite time regret minimization. And we will compare this with the available strategies. But how? Because the problem is that regret minimization is a time-varying experiment design problem, but I want to use linear time invariant tools. So how to do this? The idea is that we are going to inspire ourselves from this paper, which considers the adaptive control, H2 adaptive control, is that we are going to design we are going to do the experiment design, in different intervals of duration n. So we are going to denote n int the number of interval. And what we are going to do is that at the beginning of this interval, we are going to change the controller and the excitation properties. And then we keep the controller and the excitation property constant in this interval. Now, since we have, if we consider n sufficiently large, we can say that actually on each interval, I will have an LTI experiment design problem to solve. So that's basically the idea here. So just for the notation, so for interval number k, we are going to denote by theta hat k the estimate I have at the beginning of the interval. So this is computed by using the data of all the previous intervals. And we are going to denote by ik the Fisher information matrix. So here I'm doing an assumption that the parameter vector is distributed normally. It's asymptotically distributed normally. But with a large assumption for the number of data, we can say that it is actually normally distributed. So for the notation, we are going to denote by Vk the external excitation I apply to this to my system during interval k. I will have the input uk, state xk, and the noise ek. And here in this presentation, I'm considering the certainty equivalence principle. Okay, and we are going to have an assumption is that we need to start with something for this, especially for the first interval. So we are going to assume that we have an initial estimate with the same property. And if we don't have this initial estimate, you can still do an initial identification in order to get it. Okay, and the second assumption, so it's a very strong assumption, but I will come back to that one later, that for now we are going to assume that all the future controllers stabilize the loop, which is not necessarily true, but we will see how to deal with that assumption later. Okay, so now let's rewrite the regret by using this decomposition in several intervals. So basically, now my regret, I'm going to denote by Rk, the regret I have for interval number k, which is basically this expression here. And I'm going to use the fact that we have an interval with a large duration. So n is pretty big, so that then each term I have here, I can actually approximate with the L2 norm of each signal. And basically, so each Rk here will be written this way. So here you have the L2 norm with the weighting matrix on this. Okay, now we are dealing with a linear system here. And so the adaptive loop, and for the adaptive loop and my ideal loop, I can actually split the contribution from the noise and the contribution for the external excitation. So this is what I've done here for the notation. And now if I'm considering a stochastic, stationary stochastic external excitation Vk independent from my noise, I will have the split of my regret between two regrets. So we have one regret which is given by this, which is basically the exploitation regret, and it depends on my noise. And we have the exploration regret, which depends on my external excitation. So we have exploitation regret, it's linked to the noise, so it's linked to the uncertainties of the model, and the exploration regret will be more linked to the use of an external excitation. Okay, so now we are going to go a bit further more in the reformulation. So now I'm going to use a transfer function notation here. So if you have this loop, I'll just consider the classical transfer function loop that we have here. And Z here denote the Z variable, Z transform variable, sorry. And so then when n is very big, so we can assume that the transient dynamics from the controller changes at the beginning of each interval is negligible in each regret. So I can, oh, I really have a problem with this. So I can replace each term of my previous regret by the transfer function representation. So that's basically what I have here. Okay, what is nice is that now I have a clear expression of my external excitation on my regret expression. And now what we do in linear time invariant experiment design problem is that we try to express our control cost with respect to the power spectrum densities, because then we do this design based on these power spectrum densities. So now that's what I'm going to do. I'm going to write these terms to make appear these power spectrum densities. So that's the objective, reformulating the regret minimization like this. Okay. Oh yeah, one thing very important. I mean, I want to minimize something, but I want to have a convex problem because I want to have a computationally tractable problem to be solved here. Okay, so in order to make CVK appear in both terms, I will start first with the exploration regret because it's pretty easy. We have already VK, which appears here. So by using Parseval's theorem, I have my power spectrum, which appears here. So very nice. And then this D that you have here is basically this expression here. So you have the transfer function and the weighting matrix from the LQ problem. Okay. For the exploitation regret, I have to do a bit of technical operation in order to make this dependency appear. Is that, remember that, as I said, the exploitation regret is linked to the uncertainties of my parameter. And this, if you look at the covariance matrix of this parameter, basically it's equal, under some assumption, to the inverse of the Fisher information matrix, IK, which depends linearly on this power spectrum. So it's a result from this paper, but it's also in many, many different papers. But for this problem of design by interval, it's indeed shown in that paper. So now if I can make my exploitation regret be dependent for this Fisher information matrix, basically I will be done with the objective I wanted to do. So let's observe for this exploitation regret that actually, if you look at the function, its minimum is 0, and it is reached when I replace theta k by theta 0. So this comes from the linear quadratic property, so nothing new. But then, by using this observation, if I do a second Taylor expansion of theta k with respect of this function, sorry, with respect to theta k, and I evaluate at theta 0, then my constant term and my first term with the gradient will disappear thanks to this observation I made before. And so now I can rewrite my term with the inverse of the Fisher information matrix. So I just moved this term over there using the trace trick. And here the matrix W is basically the Hessian of this function evaluated at theta 0. Okay. And just the last trick I will do is to rewrite that as a linear matrix inequality. So I will just introduce this matrix, which is a positive semi-definite matrix. So here it's the positive semi-definite operator. So I add this variable, slack variable, so that minimizing the regrets and using this expression is equivalent to minimizing the trace, such that we have this LMI satisfied. So this comes from the Schur complement. Basically, coming from this to the here is just using Schur complement. Okay. So at the end, I'm done with the reformulation. I made my problem dependent on my power spectrum in red, like this. Okay, good. And now if I consider a very good parameterization of each power spectrum, I can transform this problem into a convex semi-definite programming, so which is really nice because then we have powerful tools to solve these problems. Okay, just to think, I will just rewrite a bit this term because we have two observations to make. The last estimate, so at the last interval, this last estimate will never depend on the external excitation I'm going to apply to that interval, because this estimate theta hat and int depends on the past interval and not the data we'll get from the new interval. So basically, the Fisher information matrix will never depend on the power spectrum of that external excitation, so the one of the last interval, but the problem is that it will only penalize the regret to use an external excitation. So I should set the last external excitation to 0. The second observation is to look at the first estimate. Well, the first estimate is something I have computed, I have available, so it does not depend on any of my variable here. So it's the same, I can actually remove the first term at k equal to 1 because it's a constant in this case. So I can basically remove both terms here, and by rearranging my regret and doing some change of the index, I can rewrite it this way. So similarly, but now my sum goes to n int minus 1. And here you see that I just have a shift of index here. But basically it's the same. Okay. So now let's consider a power spectrum parametrization. So here I'm going to go for a parametrization which is commonly used, which is the truncated exponential basis power spectrum parametrization. So basically, the decision variable are this scalar here, and this corresponds to filtered white noise, where the filtered white noise external excitation, where the filter is an FIR, so a finite impulse response of order m. So m here is something that the user can choose. And here W is a white noise of unit variance. Okay, and the nice thing with this also this parametrization is that since it's a power spectrum, I have to guarantee that at all the frequencies, this is non-negative. And for this parameterization, we have a nice result. So you can guarantee this if it exists a symmetric matrix such that this LMI is satisfied. So this comes from the positive real lemma. So yeah, it's a result from this lemma. Okay. And so at the end, so it's a bit ugly. I know, so I am not here in the room, so I can imagine the faces to look at this expression, but we will go through together with this expression. So it's just by injecting my power spectrum back to my problem, this is what I will get. So basically what I will get, so here this beta coefficient, they corresponds to exploration penalization coefficient when I'm using a filtered white noise excitation during the interval number k. Then here in blue, what we have is the information that I get throughout the experiment. And here, so here you have the first information matrix, so my initial information matrix. Then here you have the term of the Fisher information matrix, which comes from the noise, from the feedback of the noise. So this feedback gives us some information. And we have this term here, which is the Fisher information matrix gained by using an external excitation, because you see that it depends actually on my variable here. All these variables, so the variable L and the variable beta can be computed using discrete time by solving some discrete time Lyapunov equation. So we know how to compute this. So at the end, I have this problem to solve, but as you can see, it depends on theta 0. So I cannot solve it because I don't know theta 0. There is another problem, is that it also depends on the future controllers, which are unknown as well, and they are a non-linear function of my decision variable. And this is not really nice. So as a solution, what we could do is that we could replace theta 0 and all this future estimate by the first estimate, so the only estimate I know, so theta 1 at the beginning of the experiment. So as you can see now, everywhere I replaced both variables here by just theta hat 1, and now I can compute all these quantities and solve the problem. And once this SDP is solved, we should excite the control loop with all the signals that we have designed. So if you denote by FK opt the optimal filter you get, then that's how you should do the experiment. But one thing is that we have done this design based on this estimate theta at 1, which might not be an accurate estimate of theta 0, which means that actually the signal that we got here are not optimal for our problem. And let's do an observation, is that the future estimates are expected to be more accurate than the initial estimate. And so then this suggests to do a receding horizon design of the power spectrum densities, because basically what I will do, I will explain now, is that let's start from the beginning. So at my interval 1, I have my first estimate and its Fisher information matrix. I compute the controller, the Hessian matrix, and also the Fisher information matrix. I compute these exploration coefficients. Then I solve my SDP. I get all the new power spectrum for all the intervals, but I will only do the spectral factorization of the first power spectrum. I will get my filter, and I will only excite during the first interval my system with this optimized filter. Then, when I'm at the beginning of the second interval, I redo the identification, and all the step I did before, I do it, but now I do it with theta hat 2, which is expected to be more accurate than theta hat 1, which means that then the new design I will do are expected to be better than what I had before. So I do the same, I solve the SDP, I only take the power spectrum that I will use for the current interval, and then I do the loop with this optimized FIR filter. So that's basically the idea. So let's recap what we have to do. So at the beginning of any interval k, we have to identify the parameter and calculate the controller, compute the Hessian matrix. So here I'm going to drop the argument from now on just to simplify the presentation. We have to compute the exploration coefficients, the same with the Fisher matrices, and we have to solve the SDP. And then the spectral factorization. I will just mention something with the stability, is that here, since we have, I remember that I assume that we will have the stability, but we might be in some cases where I have actually computed a parameter vector which does not stabilize the loop. So how to check this? You could check, for instance, using the tools here. that since we have a parameter vector which is normally distributed with the Fisher information matrix, we can actually verify if this controller will stabilize all the system in a uncertainty ellipsoid given a probability alpha. So this is something that we can check. And if the stability state fails, what we just do is that we set theta hat k by using the previous one of the previous interval, and all the calculation here we do it with the one of the previous interval. Okay, but then one problem, the big problem here, as you can see, is that we have to do many things, but within a duration which should last less than the available sampling time. So, I mean, as you can see, we may have some problem of computational time here. And that's what I'm going to focus on this second part of this presentation now. But for that, I'm going to illustrate how bad it is actually. So let's consider a system with three states with these matrices here. So basically, if you look at the board diagram from the input to each output, we have a resonance system. And then for the model structure, I'm just going to parameterize each entry of both state matrices independently. So I have 12 parameters in this case. I consider this parameter for the LQ control. And then I'm going to, so here it's just to evaluate the computational time. What I'm going to do is not a good idea. So I'm going to fix the horizon for the regret minimization at 500, but now I'm going to consider the same number of interval as this horizon. So I have, basically I'm going to change at each interval the regret, the external excitation properties and the controller. So it's, of course, this is wrong to do with respect to what I explained before, because we did the assumption that n is supposed to be big. So, but this is just to try the computation time. And of course, I need an initial estimate. So we do here an open loop identification with 12 data and a white noise input of a variance equal to 1. And here, these are the computation time I got with only one noise realization. So this is when I run this scheme of receding horizon from t equal to 1 to t equal to 500, so the end of the experiment. And as you can see, when I increase the number of variables I have in my FIR for the external excitation, the computational time increase very rapidly. So we cannot use that in practice. And the main reason, what takes much time here, is the SDP. Because the SDP has many variables and also a lot of constraints, especially at the beginning, because at the beginning, you take the design for all the intervals. So the second objective of the talk is to try to reduce this computation time. And so here, I will be quick on this result. First, we can change a bit the SDP, try to simplify it. We have this exploration coefficient, which are given by this, as you remember. But we have a nice property, is that this exploration coefficient, because I'm using the certainty equivalence controller, actually this integrand is equal to a constant which does not depend on omega. And also this constant depends on everything that I already know, because this matrix P is basically the solution of the discrete time algebraic Riccati equation that I have to solve in order to calculate this controller. So the consequence is that only the first exploration coefficient is non-zero, and I know the value, and the other one are 0, which means that in my SDP, then I have my objective function, which is simplified. So that's the first small simplification. But we still have a lot of variable and a lot of constraints. I mean, as you can see, it will depend on the number of interval I have. So in my previous example, you have at least 2 times 499 constraints to solve constraints in your problem. So you can see why it took that much time actually to be solved. But what is very nice, and this is one of the contribution, our main contribution, is that we can remove many of these variables here, because we have this result, is that the solution of the SDP will guarantee that the power spectrum of the future intervals, so imagine that I'm at interval number k, then the power spectrum density of the next interval is 0. That's the optimal solution. So this is a very nice result, because all the variables which are linked to this SDP, I can remove them from my this problem. So it reduces a lot of variable and a lot of constraints as well. But there is another nice result with this. Oh, yeah, sorry. Forgot to mention, I'm not going to dive in the proof here, but basically you use dual theory to get that result. You calculate the dual problem, you simplify your dual problem, and then you calculate the dual of the dual. So you will get back to this problem with a lot of variables which disappear. Okay. Okay, and then the second condition, actually, so for the current interval, so we know that for the future interval, I don't have to excite. Now, what should I do for the current interval? Well, in some cases, the optimal solution is that you do nothing. And this, we can check it if this equality is satisfied. So quickly for the notation, so here lambda max is the maximal eigenvalue. Here T, that this matrix here is the toplet symmetric matrix for which the first row is given by this row vector. And each entry of this row vector, so it's given by this. So let's go quickly into this inequality. What we see here is that we have the inverse. So we have the Fisher information matrix at the beginning of the interval K, but we also have the Fisher information matrix of coming from the noise that I will get from the next interval. So this is basically the free information that I will get during the experiment. So it depends on this. It depends on the Hessian. It also depends on the Fisher information linked to the external excitation. As you can see, it also depends on the penalization coefficient for the regret by using an external excitation. And so basically, when does this inequality will be satisfied? So it will be satisfied if, for instance, this information matrix is very large. So this term here is very large. So basically, either you have a very accurate estimate, so you don't have to excite anymore, or you know that the noise will bring you many information later, so you don't have to excite as well. You also have the fact that you have the multiplication with the Hessian here. So what is important is to look at what we will get is the product here is really important. Is because if the main eigenvector of the inverse of this matrix are perpendicular to the Hessian, then we will make this quantity very small. And so all the quantities of this matrix will be small. So we will guarantee that this inequality will hold. What does that mean? So this is known in experiment design problem, is that you have to tune your uncertainties on your parameter such that you don't excite the largest eigenvector of the Hessian, which corresponds to your regret here in this case. Also, and that makes sense, if we have a large exploration, a penalization coefficient for the exploration, we should not excite. And finally, it will depend on the remaining number of intervals that you have to consider in your problem. What is nice about these inequalities, this is much faster to calculate than to check if an SDP has a solution equal to 0 in this case. So this suggests that every time I'm at the beginning of the interval, I should first check this inequality, because if it's satisfied, I don't have to solve anything. I can directly set my excitation to 0. So then the outline of the algorithm is like this. At the beginning of each interval, what we will do is that we identify the parameter vector, the controller. We perform the stability test, and we set the parameter equal to the previous estimate if it fails. We compute the Hessian, the exploration coefficient, and then we add this new thing is that we are going to check if this, there is a n/2 which is lacking here. We verify if this is satisfied. And if it's true, we just have to solve nothing, and we know that we don't have to excite at all. Otherwise, if we have to, we only solve the SDP, but very important, if I go back to my slides, we solve the SDP, but by removing all the variables which are linked to this power spectrum density, because we know that the optimal solution will be 0. Okay. And now just to go back to this example, but just by doing this change in the algorithm and using our new result about the structure of the solution, as you can see, we have a very important decrease in the computation time that it took to compute one noise realization. So that was not a very nice example because I have n equal to 1, which is not great to have asymptotic arguments. So I'm going to just change the settings. I'm going now to consider a finite horizon of 100,000. For each interval, I will have 1,000 data, and I will have, then in this case, 100 interval. So I will do an initial open loop identification experiment with more data because I want also the Gaussian assumption of my estimate to be true. And here it's going to be a white Gaussian noise of variance 0.1. And finally, what I'm going to do is I'm going to compare this, the new scheme, with the proposed scheme in the machine learning community to tackle this problem of regret minimization. So the Thompson sampling approach I explained earlier, and also the certainty equivalence approach, where I'm considering this type of external excitation. Because the regret here I considered is with an expectation, I'm going to do 100 Monte Carlo simulation with different realization for the noise and, sorry, it should be V here, and the external excitation in order to approximate the expectation operator. And something very important, so for this excitation, I'm going to tune A so by using a grading approach so that I minimize the regret. Of course, in practice, if I have a system, I won't be able to do that. But here, I'm just going to do it to compare with the other schemes. So here, in terms of just the final value, I ranked each method with respect to a decreasing order in the regret. Remember that we have to minimize the regret. As you can see, is that the two schemes in the literature perform worse than the proposed scheme. And with our proposed scheme is that when you increase the number of decision variable in your FIR filter, we seem to decrease the regret. So that's really nice. So now as a visual representation on how my cumulative regret evolves in the time. So in dotted blue, you have the 1/square root of t decaying exploration. The dashed black is the Thompson sampling. And then all these color solid line, they are our proposed scheme. What we can see is that one problem is that even though we minimize here, which was the objective, you can see that at the beginning of the first half of the experiment, we are doing worse, way worse. And we have actually a jumping phenomenon here, which appears. And that's not really great. And let's try to understand what's going on here. Why do we have this jumping phenomenon? So for that here, what I'm computing is the average of the excitation power that was sent on each interval. But here I'm only plotting the first 8 intervals, because the reason is that after this time instance, so after the 9th interval, the proposed scheme never excited. So the inequality I showed you earlier was always satisfied after the first 9 interval. So basically, as you can see, is that at the beginning, we are going to excite a lot. And during 1,000 iteration, while if I go back with the 1/square root t decaying excitation, I will already have a decrease of my excitation at the end of the first interval. So we have kind of an aggressive excitation here, which can explain this jumping phenomenon we see here. Okay, and just here what I'm computing, because looking at the excitation power is not enough. Since here I'm doing also some coloring of the external excitation, I'm plotting the average of the power spectrum of the first external excitation, so during the first interval. And I do that for several, for the different orders of I consider. And as you can see is that with the last one, so with m equal to 3, I'm able to tune my external excitation in the range of the resonance. So here what I plot is the half power points of the system, because remember that we have a resonance system. So with an order equal to 3, we are able to quite excite the right range where we should excite. Okay, so let's conclude. So here in this presentation, I formulate the regret minimization problem as a linear time invariant experiment design problem in different intervals. And then I use the tools that we have in automatic control and system identification in order to tackle this problem. But the problem is that what we realized is that we could have very long computation time. So the second part was to reduce the computation time by doing some theoretical analysis of the SDP. We have a numerical example where we show that the proposed scheme can beat other exploration strategies in the literature, which is nice. However, one drawback, we have seen that we have an aggressive exploration strategy, which might not be great because sometimes it can saturate the output and the input, because here in this problem, I did not consider any constraint for this. So some possible solution that could be investigated to circumvent that problem. First, we could add input-output constraint, which can be transformed into an LMI. So that would be great for our problem. Or another possibility is to consider a worst-case design of the regret, because maybe in that case, it will ask for a less aggressive excitation, especially at the beginning of experience. I'm done with my talk. I thank you for your attention.
Thanks, Kévin. So any questions in the cloud or in the room?
I may try one.
Try.
Thank you for the presentation. Thank you, Kévin. It was quite dense, and I guess we have to check some of your equations. I do have maybe two questions. One is very simple. In the slide 7, when you show the regret function as a difference between two quantities, is the regret function a norm? I mean, what guarantees that the difference is positive?
It's the LQ. I mean, if you look at the asymptotic regret, so for large T, basically you will get back the LQ control cost times your horizon. And so we know that in this case, the LQ control cost will be always non-negative.
Yeah, but you have a difference between two cost functions here.
Yeah, but this is the one that I get when I applied any controller, which is not the optimal controller. So this is the LQ cost I get by applying any controller, but not the optimal controller. And this is the one I get when I replace my controller by the optimal controller. So the one that will minimize the cost. So then this guarantees that then this one will be always greater than this one. And this is because of the linear quadratic control property.
Okay, I see. I have maybe another question also, I guess easy for you. Instead of showing durations, I mean, at the end of the first part of your presentation, you are showing some huge durations. Wasn't it possible to show time complexity using a big O notation instead of showing durations?
Yeah, I could do that. I could definitely do that because we know for each step what takes the most time. So I could do that. I didn't do it here, but we could do that.
So what kind of time complexity do you have? I mean, maybe it depends.
I can tell you, for instance, one thing I didn't mention. So if I go back to the outline of the algorithm, one thing I had to tune that I didn't explain here, for instance, is the Hessian. So the Hessian was taking a lot of time. So in terms of capital O times n theta, so the number of parameters up to the power of 5, because I was using finite differentiation, and this is huge. So we developed a new algorithm which reduced this computation time to capital O n x power 3, so 2 orders of magnitude less. And also for the SDP, I mean, this is really easy. You have to count the number of variables that you have, and this will give you kind of this complexity you have. And basically, it depends on the number of intervals you have, and also the FIR order you consider for your design. If I go back to, I mean, yeah, there are several variables. Do I have an SDP close here? Yeah, so you have this symmetric matrix which comes from the a positive real lemma. So this is a variable that you will have for each interval, and the same for this matrix H, which was used to convexify this exploitation regret. So yeah.
Thank you.
Any other questions? So if not, let's thank Kévin once again.
Thank you.
I stop the recording and then